Our next speaker is Prithvi Ramesh from UBS Investment Bank. Welcome. His talk will be the generalized power of Gaussian Copula. It's not a control, that's a good idea.
Try the other one.
I try different that way.
Yeah. You try this one.
Anybody know any national engineering jokes? Probably.
Hi, is this better? Yep, I think so. Good afternoon, everyone. My name is Prithvi Ramesh. I work at UBS as a quantitative analyst, where I run a team of interest rate quants in New York. I'd like to
This isn't working. It's not working.
So anytime we have a doubt or ideas that we want to discuss. That's without much curiosity and where you'd expect someone like him to just pull out tricks and answers from his pocket, but he never did that. And he sort of gave you a question that's full view, and this had two effects on us as students. One is it gave us a peek into how he thought and how he approached problems. So teaching us not just subject matter, but also how to think. And secondly, it definitely sparked and inspired all of us to be more creative. So on that note and in that spirit, let me introduce my topic. So I'm going to be talking about a popular interest rate product called Cms Spread Options. I'll lay some groundwork on how they're typically priced in a Copula framework, introduce the concept of copulas, and talk about a new Copula function that we're developing at the moment. Okay, this clicker is not working now, sorry. Okay, I can just use the mouse. Okay, thanks. Yeah, so okay, cool. So I'll start by introducing the product, the payoff, typically how they're priced, how Copula functions fit into it. Then I'll move on to the Gaussian Copula, which will serve as sort of like an equivalent of the Black-Scholes model in this context. It'll allow us to define what we mean by implied correlations. Then we move on to another type of copula called the power Gaussian, which is described in the Anderson-Peterbarg interest rate modeling book, which allows us to generate implied correlation smiles. We'll study that in a little bit of detail to see why it gives us the kind of smiles it does, and also sort of point out potentially some limitations on the universe of shapes that it can generate and why that is. And then we'll go into the motivation of why we wanted to try and generalize it to make the universe of smile shapes a little more flexible. And yeah, that's it. Firstly, a couple of acknowledgements. Rates options trading at UBS for providing the business motivation and rationale for us to undertake this research. The quant analytics team for the framework where we could implement and test our ideas. Okay. So CMS spread options. So simply put, the product is an option on the slope of the yield curve. So you have X and Y are two swap rates observed at some expiry in the future. So it's the payoff is just an option on X minus Y. Paid upfront as the payoff is paid upfront as a percentage of notional, as opposed to actually entering a swap. So to value this, we need the expected value of the payoff X minus Y minus K positive part in the T forward measure, right? So to evaluate this, we need to know the joint distribution of X and Y in the T forward measure. So the first step here is to come up with marginal distributions of X and Y. So since this is paid upfront, it's not the natural measure in which vanilla options on these swap rates are traded. So swaptions are the liquid product. And a swaption is an option to enter into a swap struck at a given strike. So the natural measure turns out to be the annuity measure. So since we have a liquid swaption market, we know everything about the distribution of X and Y from swaptions in the annuity measure. So in order to get the marginals that we need here, we're going to have to do a measure change. So that's given by this equation here. So the expected value of any function of a swap rate S in the forward measure is the expected value and under the annuity measure of a Radon-Nikodym derivative times the same function. So there's two standard tricks that are involved in evaluating this. So number one, you have to represent the annuity term as a function of the swap rate. So one way to do that would be using a one-factor short rate model where you have a state variable R, and you can represent both the annuity and the swap rate as an explicit function of R. So this annuity is not a function of the swap rate. So now that you have both variables as a function of a common variable, you can just compose one of the functions and the inverse of the other, and you can get the relationship. So we'll end up with expected value of G of S times F of S. And this can be replicated as a sort of continuum of swaptions at various strikes. So that's the Carr-Madan decomposition. Okay, so now that we have the marginals in the T forward measure, how do you join them? We use Copula functions. So Copula function is basically something that takes an n-dimensional unit interval space and gives you a single number in the unit interval. So effectively, it's mapping marginal probability distributions onto a single joint probability. Okay, so given a Copula function, we can jointly distribute X and Y by defining fxy of x comma y as the Copula function evaluated at the cumulative probabilities, marginal probabilities at x and y. So C fxx, fyy. And once we know this, we know everything we need to know to price the spread option. We can derive the density function and do a double integral, or we can reduce it to a single integral using conditioning. So this is all standard pricing of spread options. Okay, so moving on to the Gaussian copula. So the Gaussian copula basically allows you to map your x and y via the cumulative marginal probabilities onto the Gaussian space. So we map it onto the values in the Gaussian space, which have the same cumulative probability, and then we plug them into this joint normal cumulative distribution function, phi rho. So this copula is parameterized by a single correlation number, rho. So once we've defined this, we will use this to define the implied correlation as that correlate for a given price of a spread option. It's that correlation which will be which you can plug into a Gaussian copula model to retrieve the same price. To recover the price. And by definition, if you use a Gaussian copula model to value various spread options, you're going to, and then you solve for its implied correlation, you're just going to get the correlation that you started with. So you'll get flat implied correlations, so this is analogous to the implied vols in a Black-Scholes model. So if you look at these two joint probability density graphs, this is just with standard normal marginals. A high correlation means a concentration along the diagonal of x and y, and a low correlation makes the probabilities more spread out. So one thing I want to point out here is that the price of the spread option is inversely related to the correlation, which is clear here because when you reduce the correlations, you have higher probabilities for bigger moves in the spread of x minus y. So the right region of this density graph is where y is a lot bigger than x. So x minus y takes large negative values, and vice versa on the left side. And so this picture is what we'll use to derive our intuition about how we can generate skew and smile. So moving on to the power Gaussian. So this was, as I said, introduced in the Anderson-Peterberg book, Interest Rate Modeling. The power Gaussian copula has two additional parameters, θ1 and θ2. So basically what this copula function is a product of two multiplicative terms. One is the Gaussian copula itself, parameterized by rho, and one is just a product of, so the copula defined by the product of u and v, which describes an independent component. And the other thing you notice is that the two variables u and v are split multiplicatively into these two regions. So you have a Gaussian copula on u raised to the power θ1 and v raised to the power θ2, and then you have an independence copula on the remaining factor. So we would imagine, we would reasonably expect that this copula will generate some skew and smile. So looking at the joint densities, so the plot on the top left has θ1 and θ2 both set to 1. So this reduces to a Gaussian copula. On the top right, we've set θ1 and θ2 to 0.5. So we've moved sort of multiplicatively half the variables onto this independent copula and retain the remaining half into the rho copula. On the bottom left and right, we have θ2 brought down to 0.5 and θ1 brought down to 0.5 respectively. And so just looking at the densities for a moment, the top right looks a lot like we've reduced the correlations down to about half, right? So if you look at the Gaussian chart with 50% correlation, it's sort of comparable with the power Gaussian chart with θ1 and θ2 0.5, except that this one appears to have slightly fatter tails. Right, and the bottom two will clearly give us some skew because the one on the bottom left, where theta 2 is 0.5, large values of y have relative to x have a higher probability, which means that low strike spread options of x minus y will have a higher price, which means that low strikes will have a lower correlation. So we expect an increasing skew shape, and on the bottom right, we expect a decreasing skew shape, which is what we see in the next slide. So those four densities correspond to these four implied correlation plots. We have the skew as expected, and the smile on the purple line, but theta 1 and theta 2 is 0.5. We see a reduction to close to 45% to 50%, which is an interpolation between the two copulas, except we also see a little bit of concavity to the implied correlations. And that's expected if we believe that the top right density plot here has fat tails, because the fat tails means you'll have we'll have extra smile in the spread wall, which means we'll get the opposite of smile in correlation space, which is concave. Okay, so the reason we have skew in the bottom two can be checked mathematically. You can work it out and prove that one region has a higher probability given the Copula function. But in general, one thing you notice here is that when we move from a Gaussian copula to a power Gaussian copula, anything that you do to the thetas tends to bring down the implied correlations like across strikes relative to the Gaussian with correlation rho. And there's two reasons for this. So the power Gaussian copula is a product of the zero correlation Gaussian copula and a rho correlation Gaussian copula. If you reduce both theta 1 and theta 2, so let's say in the limit, as you reduce theta 1 and theta 2 both down to 0, what you'll get is that you would have transferred both U and V completely onto the zero Gaussian copula, zero correlation Gaussian copula, which makes them independent, which decorrelates them completely. And then the other way by which we achieve decorrelation is by causing a divergence between theta 1 and theta 2. So let's say we kept theta 1 at 1 and we brought theta 2 down to 0. What we would have done is to completely decouple the two variables. So we're basically moving V onto the zero correlation copula and U is retained in the rho correlation copula, which effectively gives you U times V, which describes the independence copula. So we have two different ways. So basically, whether you bring both down together, you bring one down all the way, you'll end up with full independence. So the observation here is that implied correlations come down no matter what you do. And then along with the fact that we have fat tails in the joint distribution means that the wings come down with greater convexity than we at the money. So what you end up with is a concave shape. So this is what we refer to as sort of limitation in the scopula. And our goal in generalizing the scopula is to be able to fit convex smiles and convex implied correlation smiles and allow for maybe even S shapes where we have convex and concave regions. Okay, so that brings us to the generalized power Gaussian. Okay, so sometime last year when the yield curve was not flattened completely and spreads were positive, we found that using a Gaussian copula calibrated to at the money spread options would overprice low strikes and increasingly overprice low strikes as we went lower and lower. And what we really needed to fit the market was a decreasing convex implied correlation shape. So that's what prompted us to undertake this. So as we pointed out earlier, we have two decorrelation levers. One is to bring, basically increase the dependence, transfer both variables onto the independence copula. And second is to diverge theta 1 and theta 2 to decouple the two variables. Basically, our proposal is to repurpose the zero correlation copula by introducing an extra correlation parameter rho 2. So we make it a product of a row 1 Gaussian copula and a row 2 Gaussian copula with the variables u and v split multiplicatively exactly the same way as in the power Gaussian. Product of Gaussian copulas is discussed in one of the references as well, except that didn't focus on this power form. It was a different sort of split of the variables and tested for equity basket options. Okay, so so the idea was that when row 2 is set to a high value rather than 0, we will be able to induce convex correlation smiles by pulling the wings towards row 2 instead of 0. So the intuition on the parameters is basically as follows. When you diverge θ1 and θ2, you will get decorrelation across strikes. If row 2 is significantly lower than row 1, as in the case of the power Gaussian, then if θ1 is less than θ2, you'll decorrelate high strikes and vice versa, and you'll get concave correlation skews and smiles. If row 2 is close to row 1, so you're basically using 2 high correlation copulas, then we'll see a symmetric convex correlation smile. So basically, moving θ1 away from θ2, you will bring down the overall level, but the wings will get pulled up towards row 1 and row 2, respectively, depending on whether θ1 is less than θ2 or vice versa. And then finally, if row 1 is smaller than row 2, but not too much smaller, and θ1 is less than θ2 with the distance between θ1 and θ2 sufficiently big so that the at the money implied correlation is lower than both row 1 and row 2, then we will see a convex skew with a positive correlation slope, and then either flipping rho or theta will induce the opposite behavior. So let's look at some results. So we start with an example where row 1 and row 2 are both set at 95%. So because row 1 and row 2 are equal, we'll see symmetry between θ1 and θ2. So let's take the example which is not plotted here. The density is not plotted. If θ1 and θ2 are both 0.5, then we roughly end up with the same thing because we're equally splitting the variables between 2 identical copulas. It won't be exactly 95%, but you'll get something somewhat similar. When you diverge θ1 and θ2, we start seeing decorrelation. So as you see, so 60-40 brings it down a little bit, 30-70 brings it down more, and 80-20 brings it down even more. And we also see bimodal densities here. And I think just visually, we can sort of claim that this has thin tails, and thin tails would be associated with convex correlation smiles because it would give us a concave effect on the implied spread volatilities. So that's the reason why we see convex smiles. The at the money strike is the most decorrelated, and the wings are stretched towards the Gaussians represented by the 2 modes, which go further and further from each other as you diverge θ1 from θ2. Okay, another example where we set row 1 to be different from row 2, so 90% and 99%. So this gives us, so when θ1 and θ2 are both 0.5, again, we have a rough interpolation between 90 and 99% copulas, and we end up roughly flat around 93.5. Once we introduce a small divergence between θ1 and θ2, so in these examples, it's 50% and 70%. We induce decorrelation across strikes because of that divergence. In the case where row 1 is less than row 2, because row 1 is less than row 2, we also induce skew. θ1 greater than θ2 richens high strike options, lowers high strike correlations, and vice versa. And the convexity in these smiles are consistent with what we claim are thin-tailed distributions. And we see some inflections in the wide end, which might correspond to the far end of this density plot, where we see some blue streaks of increased probabilities. I think, yeah, that's the end of my lecture. Two references, Anderson Peterberg and Vladimir Lucic, and a disclaimer from UBS. Thank you very much.
Thank you for a very interesting talk, and it's great to see Peter's students doing so well and applying this in such an interesting and unique way. Thank you. Any questions from the audience? I think we have time for a few. Here we go.
Thank you for your presentation. Very interesting. Just a comment. The paper, the Copula that you say from Anderson Petersburg actually is called the Kudraji Copula. Goes back to 95. And the important thing is that it's made to impound non-exchangeability in the Copula function, so that the interesting piece of your talk is that you translate non-exchangeability into the smile of the correlation. So if the point is that if you take identically distributed X and Y and you switch them under most of the Copula, you wouldn't have a change in the smile. While in this case, by mixing the two, you get non-exchangeability. So the point is that with this smile, you single out the non-exchangeability part that you impound in the Copula. Okay, thank you.
Time for one more question from the audience.
Hi, thank you. Very interesting talk. Copula's got a bad rep in the financial crisis because they may well be a snapshot of interchangeable pricing in a static environment, but they don't carry dynamics with them, and typically when prices crash, there's increased correlation. Can you take your model and put time varying effects in?
Yeah, thank you for that question. I think so the context of this is to price European.
Back into the mic. Thank you.
Thank you. So yeah, the context of this work is purely restricted to European options, right? So our role here is just to be able to fit a European CMS spread option market. But in general, yes, I think this could be translated into a term structure model. This could serve as a sort of target calibration, target model for a local correlation model or a stochastic correlation model. That's something we'd want to start looking at in terms of more exotic products that depend on correlation, that are path dependent. So yeah, we definitely want to be able to extend this, not extend, but use this in some way to calibrate, calibrate to path dependent products using a term structure model. Yeah, I don't know if that answers your question sufficiently.
Well, thank you very much. Now we're going to have a break now. I mentioned before that we're on a 15-minute lag from the original program, but that has been updated in both the SQA and the NYU Tandon websites. So the same schedule for today, but just 15 minutes delayed from the original one. It's now correct. Anyway, please enjoy the break outside, and we'll reconvene in half an hour at 4 o'clock. Thank you.